Okay. Above we talked about ARP. Perform ARP requests. On the same network segment, you can directly request the destination. For example, PC1 and PC2 are the same segment. All are 1.1.1.0 network segment. You can directly request. The ARP cache table is cached locally for the current data. If every data communication, an ARP must be sent before communication. This is not optimal. Now on the internet, the number of messages sent is actually a lot. For example, I now have a relatively large message. Maybe a few G. If I watch a movie, then it is necessary to continuously send messages. Each packet actually has a specified size. That is, the message will not be particularly large. For each data packet, it has a prescribed value. We call it the MTU value of the link. I told you this before. For data, data is being sent continuously, sending from source to destination. Many messages may be sent at the same time. Keep sending. Then if every packet sent, data encapsulation. That means, for this purpose MAC is to be used frequently. If now every time before sending a packet, make an ARP request. It's not optimized. Very troublesome. So now, we designed an ARP cache table. Exist locally. You often have to send data. This ARP cache table will always be refreshed. Otherwise it may be aged out. Because it is a dynamically learned representation. This is enough for everyone to understand. So let me give you a summary of the process I just talked about. If the PC now communicates with the peer, it will compare. Is the IP address of the peer end suitable for you to be on the same network segment? The way to compare is your own mask and your own IP count as your own network segment. The other party's IP and its own mask are counted as the other party's network segment. Please pay attention. What we just said. They work out the same. They go through. But it's not work out the same. This will involve ARP. Now the data is the same. Data from the same network segment. As it can be sent. And be able to reply to it. Then before sending the data, it needs to investigate the other party's ARP first. That is to say, use ARP to investigate the MAC address of the other party. Before actual communication, it will detect the mask of the peer. Are you in the same network segment as yourself? If the two are considered to be in the same network segment now, then it borrows the ARP to achieve overall operation. That is, borrow ARP to capture MAC address. Only after that can the MAC be packaged. Then proceed to the next step. Implement this operation. Then send an ARP request. The other party will reply with an ARP response. This is the query we're talking about. But actually, before we borrowed ARP to achieve MAC address capture, first, check the local ARP cache. Everyone should know this. Certainly, ARP must be sent the first time. But the follow-up will first look at the ARP cache. Wait a minute to show you. In the current cache, if there is a corresponding relationship between the corresponding IP and MAC address, now you can directly encapsulate the data. If there is no local cache, then ARP will be used to capture the address. Let's take a look together. Still PC1 and PC2. Let's look here first. I make a mark here. Everyone will find. There will be no more packets. Let's ping now. Here it reappears a set of ARP. The content is the same as above. It's all a request. Then a reply. But for the following. Now. The 5 packet encapsulations have been completed. That is, we pinged. Ping back. ARP is back again. ARP is now aged out. So let's do a new test now. Watch carefully. I'm still here to make a mark. Now if I take PC1 to ping PC2 again. This yellow ARP will no longer appear here. Only pink messages will appear. I only send ARP now that there is no local cache. Then after sending, there is a local cache. Save the 005079666680 corresponding to 1.2. I won't post it now. Let's test it. Ping 1.1.1.2. Okay. We captured new data. But in this data, it seems that it really does not have this group of ARP packets. This is the markup I just made. The only thing left is the message of the ping command just sent. There is no ARP. Actually, when it is packaged, I have found that there is a MAC corresponding to 1.2 in my cache. So it directly encapsulates. If the lookup table does not, it will do this. Next, let's talk about some slightly more difficult. For the gateway, if it is the same network segment, then communicate directly. If there is no local, just request the MAC of the corresponding destination IP. But let's think about a question. What if it is across network segments? ARP message is a broadcast message. It is delivered within a broadcast domain. The second floor is all F. But for routers, each interface is a broadcast domain. That is, if the future PC wants to send from 192.168.1.100 to 192.168.2.100, that's actually going to the opposite end. May I ask how to package the MAC for this purpose now? ARP is now a broadcast packet. But each interface of the router is a broadcast domain. This is the range to which broadcast packets are delivered. That is, if PC1 sends an ARP request now, only this interface of the router can be reached at most. It won't be forwarded here. This device cannot receive the request from the device on the left. Then it will naturally not reply. Logically speaking, if it doesn't reply, there is no way to encapsulate the second layer. If now they are data forwarding across network segments, then the second layer will encapsulate the MAC address of the gateway. PC performs calculations locally. Compare whether they are on the same network segment. It finds that it is not in the same network segment as the peer device. So now when it is sending ARP packets, no request to the peer device. Instead, request the MAC of the IP address of the gateway. That's what we just said. The target IP in the message will become 1.254. Target MAC is the MAC that requests the interface of the gateway. Because for PC access across network segments, it will go to the gateway. This is its gateway. Then since the PC now knows it is not in the same network segment as the peer device, as long as there is now a gateway is configured on the PC. It goes to the gateway. It will not find the address of the peer device. It will directly request the MAC of the gateway. The gateway will respond accordingly. So if the data crosses network segments, actually, the data will go to the gateway. It's here to help you forward. The same goes for the return packet. If the PC is now accessing across network segments, it goes to request the MAC of the gateway. When it requests in local ARP cache, the MAC corresponding to the IP of the gateway will also be cached, forwarding across network segments in the future. I will directly encapsulate the MAC of the gateway, forwarded as the destination MAC. That is, when the PC is accessing across network segments, the broadcast gateway will give it a unicast reply. For cross-network communication, it directly finds the gateway. When communicating on the same network segment, it will directly find the peer device. So everyone should know the importance of the gateway by now. Now you may not have a good understanding of the gateway. Later when we start talking about routing, gradually everyone will have a deeper understanding of it. ARP request for cross-network communication. Gateway. ARP request for communication on the same network segment. The question is directly on the other party's device, because it is the same network segment, so it can be directly accessed by ARP broadcast. The other party can reply, because it involves a data encapsulation problem. So ARP is very critical. In fact, we sometimes refer to ARP. There is another thing. Gratuitous ARP. It has another name. Gratuitous ARP. Let me show you. For example, this is PC1 and PC2. Let me modify the IP address of PC1 just now. Change it to 1.1.1.3. 24-bit mask. Let's make another mark here in the message. Wait for it to send a new message from below. Let's take a look. I am making a modification now. You see I didn't ping. Just change the address. The following packets are captured. It will also send data packets if the address is changed. Send 3 gratuitous ARP packets. This report also has some characteristics. Let's move it up. We open this message. The characteristic of this message is that when it is in 3-layer encapsulation, it is also an ARP. But it's just that this ARP is special. Its sender IP is itself. Target IP is also itself. Equivalent to. It configures an IP address for the interface. This interface only needs to be configured with IP by default. We'll send out packets. Make an ARP request. Request is. The destination IP is the same as the MAC address of the device. Now this is 1.1.1.3. The reason why we still have to request 1.1.1.3 is to do a duplicate address detection. This is what it does. The role of gratuitous ARP is duplicate address detection. I ask you a question. If the PC sends a data packet now, destination IP is itself. Target IP is also itself. Now the peer has received. For example, PC1 sends a data packet to PC2. PC1 is configured with an address of 1.1.1.1. PC2 is also 1.1.1.1. After PC1 is configured, outbound packets PC2 received need to reply to PC1. In the same way, for the current device, it received an ARP request, should give a reply. We just configured 1.1.1.3. So it will reply 1.1.1.3. So in theory, if in an environment, if your configured IP address conflicts, then you will receive a reply from a person with exactly the same name as yours. If you don't get a response like this, it means you have no conflict. So, it is used for duplicate address detection. So how does it work? After an interface is assigned an IP address, gratuitous ARP. So whether we configure it manually or automatically issued IP, it will also send. You will learn DHCP later. Dynamic Host Configuration Protocol. In the whole environment, this IP is unique, because as long as there is no conflict, no device will reply you. If there is a device to reply you, just to prove it's the same as your name, you need to change your name. When data forwarding is performed as a whole, it is not acceptable for two devices to have the same name. Let's move on to the next question. This problem is a little more complicated. Let's add a few devices now. Add a router. Then add two PCs. What we want to do is an extension function in ARP. Proxy ARP. We first make a connection to them. Relatively speaking, it starts up pretty fast. Let's refresh it to open it. We also turn on the device. After opening, we are going to make a configuration. Then, before configuring, first of all, we need to plan the addresses for them. I took it to the drawing board. We plan the address. What we do today is not cross-broadband. We are doing the same network segment. Suppose the IP address of the PC on the left is 192.168.1.100. Sometimes you may find you forgot some configuration. For example, if you forgot to configure the gateway, suppose the IP address of the PC on the right is 192.168.0.100. 23-bit mask. Actually, for ARP proxy, when you refer to static routing in the future, point out the interface. It will also have some relationship with. Only, nobody uses that thing like that anymore. For now, it is not very common that the host does not have a gateway. Although this feature is very useful, can solve the corresponding problems. But in fact, we are now configured to do. I hardly ever use this feature much. Let's take a look at what it can do. On the left is 192.168.1.100. On the right is 192.168.0.100. Let's also configure the interface on the right. Suppose the interface on the right side of the router is 192.168.0.254. The interface on the left is 192.168.1.254. They are both 24-bit masks. This is the respective gateway representing the PC. But we don't configure the gateway for a few days. If we access across network segments, in fact, the gateway is to be configured. Let's configure them. First, think about a question. For this scene, are the two PCs on the same network segment? PC2 is 192.168.1.100. 23-bit mask. PC3 is 192.168.0.100. 23-bit mask. Now for PC2. 192.168.1.100. The mask is 23 bits. The network bit representing it is 23 bits. The last 9 bits are host bits. Then whether it is 1 or 0, both are 24th. They are both on the same network segment. I forgot to write a space here. Reconfigure 192.168.0.100. Okay. The two of them are actually on the same network segment. All in the 192.168.0.0 network segment. Then we configure the network segment. You can check it out here on PC2. Now I have not configured a gateway for it. That is, now gateway is empty here. I only configured an IP address and mask. Gateway not configured. Gateway is empty. Then for PC3, I did not configure the gateway. This means that if data access across network segments, I can't access. So now we go into the router. Enter this interface. We configure it accordingly. This will be slightly slower. We enter configuration mode. Then enter the interface. The one on the left is the 00 interface. We configure an IP address. It is 192.168.1.254. Then we configure the mask. 3, 255 and 10. Because it is a 24-bit mask. Followed by no shutdown. Enter the 01 interface. We also configure an IP address for it. It is 192.168.0.254. The mask is also 3, 255 and 10. We also give it no shutdown. It is now configured. Let's walk through the process. As a PC, let's see what it should do now. Before that, we still have to capture packets. But I turned off other environments before. Because this is the previous configuration. When we captured on the left and right interfaces of R1. First look at the 0 interface on the left. After that, it is also opened here on interface 1. That is, we now capture one interface. Open both. After we open it, let's go on. For the current experimental environment, let's think about the process. First ask everyone. If the left PC pings the right PC, can you ping through? What we say now. This is the 0.0 network segment. This is also the 0.0 network segment. Both are on the same network segment. If the PC now judges that the other party is on the same network segment as itself, it should send ARP broadcast directly to the other party. Query the other party's MAC. For example, before the PC wants to ping each other. To encapsulate the second layer. I don't know the other party's MAC now. The PC must first send an ARP packet to ask MAC. But the embarrassing thing is, they are indeed on the same network segment. And for routers, the left interface is the 192.168.1.0 network segment. The right interface is the 192.168.0.0 network segment. The two interfaces of the router. Not in a network segment, but for PC. Overall, can be on the same network segment. For PC1, they are on the same network segment. For PC2, they are on the same network segment. But for routers, these are two interfaces. Now you will find the overall network bit of the two PCs is too short, causing them to cover a larger range of network segments. But for routers, network bits are too small, causing them to have too narrow a segment range. You will find, in theory, they are both right. They are both in the same network segment. These two are in the same network segment. And for the router, these are two network segments. We don't talk about switches. A switch in the middle. This is the same as a missing switch. Both of them cannot be pinged. We just said, PC2 sends an ARP broadcast to ask. But unfortunately, ARP broadcasts can only be forwarded under one broadcast domain. For the interface of the router, each interface is a broadcast domain. That is, now this message can only send to this location at most. This ARP request cannot be sent to the other side. Let's test it first. It is now 192.168.1.100. Ping 192.168.0.100. Let's take a look. We can find out that it seems to work. In theory. It should be unreasonable. How come it works again now? That's another question. First of all, for the router. Let's first look at the left interface of the router. Everyone will find. Indeed received ARP packet. I stopped it. Don't worry about the other ones what they are. What is asked in this ARP packet is, who has 192.168.0.100? Call 192.168.1.100. 1.100 is the PC on the left. 0.100 is the PC on the right. I cut this picture. Look at. Because we follow the message. To analyze it will be more accurate. Let's look at this picture. Now PC3 is 0.100. PC2 is asking PC3. Then now you will find. The device got a reply. There is now an ARP. This is called ARP request. Is a request message. The following is called ARP reply. Is a reply. Now it receives a response. And it got the MAC address of 0.100. That is. It gets the MAC of the right PC. Let's take a look. Is this MAC the MAC of the PC on the right? We go into this PC3. Check its MAC address. We will find. This is not the MAC address of PC3. PC3 is 005079666803. It now replies with AABBCC001000. It's not a PC3 MAC. In the process, it goes to request PC3. But PC3 did not reply to PC2. But it does get a MAC address like PC3. So whose MAC address is it? It must be real. Now the left PC is requesting the MAC of the right PC. It did get a reply. Now the MAC corresponding to the PC on the right is AABBCC. But we looked at the device's MAC. Found that it is not the MAC address. So, whose MAC address is this AABBCC? Okay. Is the 00 interface of the router. In fact, we don't have any other interface now. A total of 4 addresses. Both of them ruled out. Now there are only 2 of them left. It feels like this address. Because the MAC address works on a link. So is the address of this interface. So it replies pretending to be PC3. Let's check the current interface of the router. We have to get out first. For example, I am now checking a layer 2 interface. I'm going to see Ethernet. It is the 00 interface. Let's see what's written here. Address is AABBCC001000. This looks familiar. This is the 0 bar 0 interface on R1. It's a MAC address. This is what we are answering now. AABBCC. That is. The router uses its own interface to impersonate the address of PC3. Reply a MAC address to PC2. The proxy function of ARP we talked about today. It is enabled by default on Cisco devices. So when the PC sends, it is able to help forward by default. Okay. We just looked at the message on the left. Let's now look at the message on the right. That is the interface on the right. I pause. Start here. A message is now sent. PC3 is 192.128.0.100. Tell 192.168.0.254. So it is. Who has PC3? Right interface of tell router. Because this is the packet captured under this interface. It is equivalent to another ARP request now. Is sent through this interface. Then the corresponding PC3 replied to it. 192.168.0.100. is at 005079666803. Here is the real MAC address of PC3. The device on the left asks the router. The router replies with an interface of its own. Then the router asks the device on the right. The device on the right puts the real MAC. Told the router. When the final forwarding. The device on the left sends data to the router. The router helps forward the device on the left encapsulates the MAC of the router. The router encapsulates the MAC of the device on the right. The PC now interacts with the left and right interfaces of the router. This is an interactive process between them. Then we make a simple summary. Let's continue to look at this picture. For routers. Proxy for ARP on Cisco devices. The interface is to enable the proxy function of ARP by default. Then when PC2 sends a request to the left interface of the router, it requests a MAC address of 0.100. When the device receives an ARP request, if the target IP it requests is not it simply drops the packet. But now the router will not drop the packet directly. As long as the ARP proxy is enabled on this interface, it will not directly drop the packet. It will look at who the message is looking for to ask for the MAC address. It is now looking for 0.100 to ask for the MAC address. Then it checks to see if there is any. If so, it will reply to it. But if not, it will activate its own ARP proxy function to help the equipment. Certainly. It's also not the actual PC that replied. It also responds to this interface. Otherwise retweet. There is no way for you to package the MAC. In the next paragraph, the reply is also this interface. It's just that it involves the question of asking again. Not everything. The router itself has to be able to. I give an example. Suppose you have a question you can't do now. You think I will do. So you need to find a good person to ask. But you don't actually know where this guy is. You send this data packet. Can't even get to this place. The data packet arrives at the router in the middle here. It doesn't know if it will do it. But this data packet arrives here. Logically speaking, the router is not the guy you're looking for. It won't know your question. It drops the packet. Then, for the device. Since the device has proxy function enabled, it's like it's now helpful. If you now send a packet to it you have to ask it a question. This question it won't. But it can help you ask. Ask the person you want to ask. But the premise it asks is, it knows this person. It's the same in this picture. The data is now going from 1.100 to 0.100. Since PC2 is now requesting 0.100. Router is not 0.100. It will help PC2. Not directly discarded. It goes to help PC2 ask PC3's MAC. But only if it knows where the device is. That is, it has to be connected to PC3. It needs to have a route to PC3. If now a line connects the devices at both ends, an address is configured on the left. An address is configured on the right. The right side is called the direct route on the left side. A direct route will be generated on the router. Since we are now going to visit the network segment of 192.168.0.0, it is a direct route of PC2. So it can reach. It's okay if you don't understand here. Because many knowledge points in the course are coherent. So it is easy to encounter knowledge blind spots. When we talk next class, let's have a deeper understanding. Here is a direct route. There is also a routing table. There is this representation in the routing table. Prove that the router can reach. PC2 now sends a message to the router. It doesn't matter. Although this broadcast packet can't get through, the router can help PC2 send another broadcast packet to request. Because this broadcast packet can pass is due to the isolation of broadcast traffic by the hardware. This router can't help PC2. All it can do is help send another packet. Help to ask. This is what we call ARP proxy. It will help to send another ARP. Then when this ARP is sent, just use your own MAC address as the source. I went to PC3 for the address. Later, form an ARP cache locally. But although there is a local cache, but it won't cache this to PC2's. That is, PC2 is requesting a MAC of 0.100, while the R1 has gotten its MAC. It also doesn't tell PC2's if the left device. It is really packaged by the MAC of the device on the right. PC2 is under this broadcast domain. Can't reach PC3. What we call encapsulation based on MAC address. It is performed under a broadcast domain. It is a concept on the link. PC2 cannot find the peer device, so it can only find the router in the middle first. Let it do a retweet. All data encapsulation required. The router will have an ARP cache. ARP cache it corresponds to. It is a correspondence between an IP address and a MAC address. Then everyone has to think about the corresponding relationship. As long as a device wants to send data. Data encapsulation. Just perform data encapsulation. IP address and MAC address must be encapsulated. Then as long as you need to encapsulate, then there is ARP cache. So the ARP cache is present on all devices that will communicate over the network. Whether PC, router, firewall, switch, all have ARP cache. Certainly, the switch has to be a layer 3 switch. Otherwise, you don't even know what an IP address is. There will be no correspondence between IP and MAC. Let's take a look. First, the two PCs can be pinged. This is what we have verified. We can do a verification on R1. Let me check. ARP on my device now. Okay. Everyone can see. For me now, I have a corresponding ARP on my device. And the information I got is correct. In addition to the interface on its own body. It does not count. This is 0.100 for MAC. This is 1.100 for MAC. The one on the left is 050079666803. The one on the right is 005079666802. We can also take a look here. 005079666802. This is the left PC. Let's check ARP on PC1. Everyone will find. Here there is 192.168.1.0. That is the ARP of the right PC. This is what we just demonstrated by capturing packets. The left PC thinks. Now the address of 0.100 is AABBCC. Data encapsulation. It is encapsulated like this. For PC2. It does not know that. The router has opened a proxy function to help itself. It thinks they are on the same network segment. PC3 reply is the same. It thinks they are on the same network segment. PC is unaware. Middleware help is a function that it enables. The PCs at both ends regard it as a mutual access on the same network segment. To us. It also doesn't have to be a physical direct connection. It's not necessarily connected by a single thread. It may also be connected through a switch. Anyway, a network segment is directly connected. As for passing through the router in the middle, they don't know. Okay.